Let's talk about composition of functions. This is a quick review of composition from a few points of view and a few kinds of metaphors for composition in preposition and preparation, not preposition, in preparation for looking at the chain rule in calculus. That's the main goal here. You don't have to know any calculus to do this, though. So one of the most important pictures of composition of functions comes out of the sort of black box kind of machine picture of a function. That if you have a function, it has inputs and outputs. That's the basic nature of what a function does. It inputs a number, does something to it, spits out the output. And we could understand it graphically, or we could understand it with a table, 0, 1, 2, 5, 7, 3, whatever. Or we could understand it with a formula, maybe g of x equals x squared. Okay? Lots of different ways. Anything that relates inputs to outputs. Okay? So given that understanding of a single function, what it means is that an extremely natural thing to do, in fact, the most fundamental thing you can ever do with a function is, let me give a little more room here. Let me put it down here. Is to take the output of this function and to stick it into the input of another function. And we want to have names for all these quantities. Input of the first one, let's call that x. It's a pretty standard name, but we don't have to use x, and we often won't. The final output we often want to call y, because what we'd like to do is just think of this as one combined function. But we need a name for the intermediate, and u is often a very popular name for that. Okay, so we can express this in equations as u is the output of g, the function g, when x is put in, and y is equal to f of u. Y is the output of f when u is put into it. And believe it or not, having all 5 of these letters can be very, very helpful. Sometimes we're going to focus on the names of the functions, and there's ways of expressing, for example, the chain rule using only those 2 letters. And then sometimes we focus on the variables. Okay, so that's worth writing down. There's sort of 2 perspectives. Focus on the names of the functions versus the variables, and we really need to kind of master both kinds of ways of thinking, both kinds of notation. So as an explicit example, this could be like the square function, and this could be the sine function. Now I don't want to write sine of x here. I could, but that would be a little confusing because I've already reserved x for the input of this guy. So let's say sine of u. Okay. Then what would the combined function be? Oh, you can't really see that y very well, can you? Let me zoom out. My camera faded down a little bit overnight, looks like. So what would be the combined function? One way to think about it is I've got this 2-stage process, like an assembly line, and I just want to put it in a big warehouse, and I don't want to look inside the warehouse. I just want to have one step that says, okay, don't worry about u. I just want to go from x all the way directly to y. Well, then that's going to be y is sine of u, but u is just x squared. And so that's a function that's the composition of these 2. Okay. So this metaphor of the machines combined into one big machine, or like often I think of an assembly line with lots of little things, and we don't care about the details. Let's just give us the final formula. That's a nice metaphor for a composition. Okay. Well, there's another one that I find useful when we're thinking very algebraically. That really gets at the structure of inputs and outputs, which is really fundamental. But there's another one. Suppose I had this equation I wanted to solve. Suppose I had 2 equals the square root of e to the x squared. And I wanted to solve that. Well, secretly, that's a problem about function composition as well. I'm going to switch to blue because it might be better. Okay. And I want to look at this as this is a composition. It's a triple composition of 3 functions. And here's another picture I often use, especially when algebra is concerned. And it's also very useful for calculus when we start looking at the chain rule in a very algebraic way. I start out with x as the kernel, the core of like an onion. The first thing that's done to x is it becomes x squared. So that layer includes the squaring function. Then it gets even more complicated. I take that x and I plug it in to the exponential function. I get e to the x squared. And then the outer layer here is the whole thing, square root of e to the x squared. You can't really see that very well, can you? Let me make a really big space for that. Square root of e to the x squared. Of course, this is exactly what's here. Okay. And this is what I would call the onion picture. And the reason that's useful is that especially when you're solving equations, what you're doing is you're just stripping off layers of the onion. Okay. So to solve that, we just strip off the layers of the onion. Okay. So what does that amount to? Let me see if I can squeeze it in over here. Okay. You strip off the first layer by squaring both sides. And hopefully this is familiar, not incredibly weird, but I wanted to point out that it really is actually thinking in terms of compositions. So you've stripped off that outer layer. In the machine picture, that would be the last leg of the last thing in the assembly line. Now we are going to, what's the outer layers? This is where it's really useful. Do I square root now, or do I take a logarithm? What do I do? Well, I've taken this away, and it's as if that never existed, and I'm dealing with this simpler composition, one stage less. But what's the outer layer? It's the exponential function. That would be the last thing I did if I put in an explicit x and actually figured out what e to the x squared was. I'd take like 5, I'd square it to get 25, I get e to the 25. It's the last thing to do to evaluate. That means it's the outer layer of the onion. That means it's the next thing to do to strip off. Okay, so I need to take the natural logarithm there to undo that. So I stripped off that layer. Okay, now I'm just dealing with a function x squared, and that's not too hard to deal with. X is plus or minus the natural log of 4. Okay, which is about plus or minus 1.4, roughly. Okay, so that picture of stripping off layers, and especially the idea that once you've stripped off a layer, like here, the square root has completely vanished from the picture. That's going to be true in calculus as well, that we can kind of do things layer by layer, and we don't have to worry about the outer layer once we're done with it. One other observation is one thing I had in this example is I had a square and then an exponential and then a square root. The square root and the square root absolutely cannot be canceled from those. Okay, one of the things that tells us that is it really matters what order the layers go in. It really mattered that I squared and then exponentiated and then square rooted, and not in some other order where the square and the square root might be next to each other. They were not next to each other. They do not cancel out. Okay, so that's another metaphor that we're going to use a lot, the metaphor of the onion and the layers. And let me give you an example that's not algebraic at all. You know, this blue marker it used to be my go-to marker here. Okay, non-algebraic meaning I'm not going to give you any explicit functions, and maybe I'll draw some graphs. Okay, and this is an example I always come back to again and again. I have a bug crawling on a rod, and so the bug crawling, that has a position function, and let's say the position s is g of little t the time. That's our standard kind of example, especially in calculus situation. Position is a function of time. And then the rod, let's say, it has some warm and cold spots, and its temperature, big T, is a function of the position. So here's the rod, and maybe it's cold over here and warm over here. Okay, so what would composition have to do with this? Let's do another color just for fun. What if I look at the temperature as a function of time for what the bug experiences? That's exactly a composition. That is, you look at, like, one metaphor for this, for example, would be there's a bunch of different thermometers at lots of different intervals along the rod. That gives you the F of S information. All these different thermometers give you various numbers for how the temperature varies as a function of where you are on the rod. So this is the function that tells me if I know the position, I can get the temperature. But wait, if I'm the bug, my position is given by G of T. So this is exactly this situation of you give me the time, first I have to access this function to figure out where the bug is, then I have to access this function to figure out how hot that spot on the rod is. Okay, so this is going to be, I don't really need this anymore, do I? It's going to be the same situation where I have T, it goes into this function that talks about how fast the bug is moving, what's the position, where it is at a given time. That gives me the position. That was what I was calling U before. And again, the letters don't matter, so I wanted to make sure I did an example with different kinds of letters. And then the F is all this thermometer data that tells me if you tell me a position, I can figure out the temperature. The shortcut function is this guy, which is the temperature as a function of time. Okay, so let's think about that a little bit in a sort of graphical example. And then this video will be over pretty soon. It's not supposed to be too long. So suppose I had this kind of situation where here's the function g. He starts at the left end of the rod, s equals 0, goes to the right end of the rod, and then very quickly goes back to the other end. And let's say one of the spots he goes through is s equals 5. Ooh, we can't tell the difference between my 5 and my s very well. There we go. Okay. And then here is the temperature as a function of position. That's the function f. Let's say, just like I had before, that it's kind of cooler over here and then like this and then maybe warm over here. So as I go from left to right along the rod, let's have the rod again. Then that's from cool, low values of s, let's say s equals 0 is here, are cool, and then warm over here. And let's say s equals 5 is right here. Let's say maybe right here. Okay, s equals 5. Okay, so what would be happening to the, let's see, so now I'm going to have to erase this even though this is kind of key to the next step. What would the temperature look like as a function of time? Well, so as time goes on, first the temperature, let's say this maxes out at like t equals 2. Let's probably need that. As the time goes on, the position is increasing for a while. So he's starting over here and he's moving over here from the cool to the warm. And so he's sampling higher and higher s values all the way through 5 and beyond, maybe up to about here. And so his temperature is going up, up, up. And I'm not going to draw it super accurately until he gets to t equals 2. And then he starts moving leftward. The s decreases. He's gone past s equals 5. And he starts moving leftward. And that's going to be going down on this curve. And so he's going to be going down like this. Oh, and steeper, because his motion was steeper. And so that's going to happen faster. And in fact, that's really part of what the chain rule is going to be about. In particular, let's look like right here. Let's say this is t equals 1. What's going to influence how fast the rate of change of temperature with respect to time is? So this is the calculus part, if you want to drop out if you haven't had any calculus. What is this going to be influenced by? I'd like to know how fast the final variable changes. What's the rate of change with respect to this initial variable, little t? And I might need to know how that's related to this intermediate variable. And so you want to ask yourself, what's going to affect how fast the temperature is changing as a function of time? And let's not worry about it too much in terms of math or graphs. Let's just think about it commonsensically. As the bug is moving at t equals 1, he's at this location. What's going to affect how fast he perceives the temperature to be changing? It's probably going to have to do with how fast he's moving, which is the slope of this graph, and with how sensitive the temperature is to a change in position. If this was flat and the temperature were constant, this would be 0, no matter how much he moves. If this were flat, so that he wasn't moving, then no matter how much the temperature changed from point to point, this would be 0. So it's a combination of these two slopes, and one of the properties that's fairly clear is that if either of the numbers is 0, this should be 0. That already gives us a pretty good guess as to what simple formula might relate these two slopes to the slope of this guy. And that's where we're going to get to the chain rule.